So welcome to this part one of the Take Flight with HIL webinar series. Today is part one. So our topic will be how hardware in the loop testing can help you take flight. So welcome everyone. Let's start. So a little bit on the upcoming webinars that we will be hosting. So in the blue zone, the Take Flight series. So the second part will be held on October 24th, which will be focusing more on the electrical systems, aircraft electrification, and finally part 3, which will be held on November 14th, and which will be a fireside chat where you can discuss testing trends and challenges, and will have some people that will be here to answer questions and move forward with your ideas. A little bit about OPAL-RT. So basically, we've been here for about 27 years, about 425 employees worldwide. You see the map. Orange is our headquarters, blue are our offices, and in gray are distributors around the world. One important part of OPAL-RT is that we reinvest 20% of our profit in R&D each year. And why are we talking about aero today? Is mainly because the market segments that OPAL-RT tackles or services is power systems, power electronics, automotive, and aero, obviously. So let me introduce the speakers for today. Yours truly, Alexandre Leboeuf. I'm the Aerospace Business Unit Manager at OPAL-RT since the last 4 years about. I've been working with OPAL-RT for the last 16 years in system integration and testing. And I have an electrical engineering background and been working worldwide to support the aerospace business for OPAL-RT in the recent years. With me, I have Ashok. So Ashok, welcome. Can you present yourself a little bit?
Yeah, of course. Thank you, Alex. Welcome. So Ashok Debian, I am Director of Research and Development in a French company called Certia for more than 25 years. I am expert in mechatronic systems, and in terms of background, technical background and studies, I am more involved in automation, robotics, and the computer system and mechatronic systems. And I have also this ability to manage a complex project, like our project in Certia, and also manage different competencies in my teams. And maybe a few words about Certia in the next slide.
Of course, there you
Certia
go.
is a French company established in 1987 in Noisy-le-Grand, which is in France. Our activities in engineering, tooling, test rigs, test bench, and for the aerospace, but not just for aerospace industry, but also for the automotive and defense industry. We have a heavy and a big capabilities in terms of research and development, and we spent more than 20,000 euros per year in the field, the different fields, mechanic, engineering, computer science, and so on. Our main customers in the aerospace, we have Airbus, Safran Group, Leonardo, which is Italian company, Comac, the Chinese company, Collins, and the different aeronautical actors, if I can say that. We have also a client in the automotive like PSA, Hitachi, and the energy, the French provider of the energy, EDF and Westinghouse, nuclear company. We have also activities in the defense and also the research and development program. So if you need to know more about Certia, you can just go to the website certia.fr.
Awesome, Ashok. So I understand that Certia is present worldwide. You're not present only in France, right?
Exactly, yeah, correct. We have our customers in North of America, in China, in Australia, in Africa, and many countries in Europe.
Thank you, Ashok.
Thank you.
So let me introduce you to the main topic of today. Right now, let me entertain you a little bit with some, perhaps a recap for some of the theoretical aspects of testing and how it's gonna be tied to today. And after that, Asho will be presenting us a program of an application of all of this. So let's start with the evolution of embedded software in aerospace. So the commercial aircraft that we've been using for the better part of the last 10 years or so have about 6.5 million lines of codes. So if we take into account that we usually find 10 to 20 defects per 1,000 lines of codes, this tells us that we might expect somewhere about 65 to 130,000 of errors in the code. So it is pretty impressive. So obviously we need to test to make sure that those errors won't be impeding on the security of the aircraft and most importantly of its passengers. So if we take a look on the upgraded or more complex system, like for example, this KC-390 Embraer transport military aircraft, it has about like 25 million lines of code. So obviously the defects rise accordingly. So when we move towards the new generation of aircraft, the eVTOL, the full electrical and the full autonomous aircraft, you can only imagine how many million lines of codes there will be. We don't exactly know yet because most of the aircraft aren't even in production yet and are only at the prototyping phase. So testing has never been required as much today. So let's move to the traditional V model. Most of you, I think, have an idea or have seen it at one point where you take the needs, you do the design, you have the physical aspect and validation of your prototype and the putting the solutions into products, into services that can be sold to your customers, right? So this is known, it's understood. But let me present you a new version of that V model. So basically, it becomes the diamond model. What is the diamond model? Since the coding part of all the aircraft is becoming a very predominant aspect of the design phase, companies have started to create a full environment and validation methodology for the coding, which is named digital twins. So they take their models, they simulate the overall system, the overall aircraft, to be able to make sure at the earliest stages possible how the software is debugged, validated, serviced, and after that, integrated into the physical aspects. So you're asking me where HIL fits in all of that? Is most HIL platforms nowadays obviously can help and support your physical testing, hence the hardware in the loop. But most of those platforms can also support digital twin configuration. And most of them have the scalability feature that helps you start with the digital part, so just a simulator, and upgrade it as your need evolves throughout your program to get more IOs, more subsystems, more components. So that's the part of it. So if we take on the right the electrical motor for our aircraft, so obviously you have your design parts, your code and everything that will be needed to be integrated in the aircraft. The motor itself needs to be controlled with the actuators and controllers or LRUs, line replaceable units. So let's take a look. So basically here it's our interface and what we have in hand right now. So how do we test it and how do we make it work? Okay, it's simple. We move it towards a system, a hardware in the loop system. On the right, you have the aircraft simulation and IO components. So you have the data acquisition, the instruments to do the measurements, the real switching and everything. And on the left, connected to the mass interconnect, you will have your line replaceable unit, the controller, and a real actuator that will be controlled through the motor or vice versa, depending on your application. So, okay, you have that. So how can we make it happen in the hardware and the loop system? So basically, we put everything like this inside the system to create what we see here. So basically, we move things a little bit. And voila, we have our OPAL-RT, our full integrated test solution that can now be connected to your hardware to be validated. So if you take a look into the image at the bottom, you see your electrical motor is there with the inverter control and the different components of the PMSM and the inverter that will be controlled through the LRU and the actuator that will be tied to this system. And you have your full aircraft simulation at the top right, where you have the high angle of attack mode, different type of configuration that can be used, and so on and so forth to make the full capacity of your test system. Now, Ashur, I invite you to present your actual use case. So please.
Sure, thank you. Thank you, Alex. So what is the use case? What is the context? The context is the regional aircraft. That means it's the aircraft dedicated for the short range travels. So what is the challenges is to make the aircraft cleaner in terms of, environment. We need to add new technologies, innovative one, mainly for the power and the actuation system, the different actuators. And we have to certify and the aircraft by optimizing these two, this couple between the cost and the time. And what is the solution for that? We propose it in case of this application is to use more and more onboard electrical power because it's identified as a cleaner than the hydraulic systems, which is the actual hydraulic the power on the aircraft. And the second thing, which is very interesting and very important, is to add the hardware and the software in the loop in the process of the designing, but also as alternative for the real and physical parts on the aircraft. Just to remind you that the aircraft in this new generation of aircraft are supported by the European funding and clean aviation. That is the name of the program. Next slide, please. And let's talk now about the Iron Bird. What is the Iron Bird? The Iron Bird is a testing platform. It's like aircraft zero. So we have all the component on the aircraft, but in the ground, it's not on the fly. And they mean to verify and validate all the system technologies, the new technologies, the new equipment, the new actuators. We have to verify before the first fly, support the team of design, and also verification of the integration of the system and the subsystems on the aircraft, because we have the verification at the component level, but we have also to make this verification at the architecture level, integration level, and for this reason we need to build this kind of platform, which is the Iron Bird. They represent the full scale of the real aircraft, and they support to achieve what we call the permit to fly. That means after all the testing on the Iron Bird, the Airbus, for example, or Boeing have this permit to fly, this permission to make the first fly on the aircraft in the real condition. Next slide, Alex. Thank you. So let's talk now about the traditional or the actual or the current design of the Iron Bird. So the Iron Bird usually is made at the physical level. That means we have 100% of physical components and a physical integration system. like the two pictures here. The Iron Bird integrate all the aircraft equipment. For example, on the top, we have the Iron Bird dedicated for the landing system and the bottom for the aircraft system. It's not the last pictures because we're not allowed to diffuse the pictures after after the project is achieved. And the Iron Bird is quite heavy in terms of investment because it costs several million of euros and it takes many times to finish the test. Because we have many challenges. It's in terms of time we have around 2 or 3 years to be ready to run the test. Next. And what is this new idea, the new challenges in this case? So we decide to build the first mixed Iron Bird, which is a big challenge. That means we have a first real and half simulated Iron Bird. If you see in the pictures, normally this kind of aircraft, when we have to test and build the Iron Bird, we need to have all the physical system. But here we decide to have a left aircraft wing as a real one, but the right aircraft wing, it will be completely simulated. That means more digitalization, more models, but real-time models, okay? We have to make this difference between the model to design or the model to represent the physics of the systems. And we have also the flight simulation computer, which is the model of the aircraft, aerodynamical model of the aircraft. So that is the new generation of the Iron Bird we made in our last experience. Next slide, please. Yeah. So if we can go deeply in this mixed architecture, we see the two boxes, the red and the green one. On the red, we have all the physical actuators with the surfaces, with the power system, with the physical link, even mechanical, electrical, or so on. And in the green box, we find finally the virtual wing. That means we have all the models, the real-time models of the missing actuators, of the wing, the physical, mechanical, and all physical parts on the system. And we have this connection between the two parts in order from the pilot to see just one aircraft, which is with real feedbacks. And in the next slide, I want just to conclude that this is the first formula. That means it's applied to validate and to get the permit to fly for the aircraft based on this kind of Iron Bird, which is the mixed Iron Bird. And we use it to the certification of the equipment, which is very important. The project was successful because we reduced the installation cost by 30%, and we reduced also the time of spent to test by 40%. And we can mention also that now we have like generic platform for the validation. So we can reuse this platform just by change the scales of the models through the parameters and the other things. And I think that it opens the way to the fully real-time facilities in the future as digital twin and all other other kind of application. So if you see here pictures, we have the mixed Iron Bird with the physical equipment, and we exchange with the different models, the real-time models of the missing equipment.
Thank you, Ashul. It's pretty interesting also to think that in the project success, you don't mention it, but I think since we're having half an Iron Bird, we're going to save also on square footing in the building. So it's going to be less costly to maintain and to be able to reuse that space for some other components, right?
Exactly, yeah, correct, yeah.
Awesome.
And here, just to mention, just more details about the virtual system with the different real-time models and real-time flight mechanical simulation computer, which is the aircraft models. Thank you, Alex.
My pleasure, Asho. So, just perhaps a little bit of a teaser that we can add at this stage is a little bit of the projects that we're currently working on. So, if I may, OPAL-RT projects currently are working on mostly on electrical propulsion, since OPAL-RT has a focus on electrification, which will be mentioned more in detail, which we're going to touch in the next installment of our webinar series. So the electrification, so electric propulsion with the different inverters, electrical motors, and sensor. We also have the battery management system that will be part of the charging. And we also have some of the landing gear project that we have had and a few of the eVTOL series that are presently in prototype. We're helping them with a lot of different components and test systems for, like I mentioned, a little bit of the motors, the battery, and all the implemented systems with their Ironbird. Asho, I don't know if you can give us a teaser on your end from Sarcia's point of view, your current projects.
Yeah. So I think that the strategy of Certia is, after providing 100% of physical testing facilities, is to lead this trend of the digitalization and to provide more, not virtual, but more, simulators, real-time simulator based on your solution. And we have two big projects. We are discussing with our customers about two big projects. The first one is to make the digital twin of the Iron Bird of the A400 military aircraft, which is the European aircraft. And we are discussing with Airbus about this subject. And the second one is the phase 2 of ATR. ATR is the regional aircraft provided by a joint venture between Airbus and Leonardo, which is the equivalent of Airbus in Italy. So it's two big projects and very interesting one, because I think that we finally we see that all our customers now are convenient that using the hardware in the loop and software in the loop, real-time simulation will be the future of the testing systems.
Yeah, we see that as a trend. We've seen it at OPAL-RT with other of our customers, but this means that with those very big projects, you have your work cut out for you for 2025. So congratulations, you'll be pretty busy.
Yeah, thank you. Yeah.
So let's move forward to some of the products and services that can help you take flight. So basically, the real-time simulator. So OPAL-RT real-time simulator platform is based on a Linux kernel. So basically, it allows the users to install and custom design their own packages to be implemented into the system. So like for Ironbirds, if you have like a system that interconnects all your test benches, but it's a proprietary component, it's easy to integrate into a real-time simulation platform. After that, signal conditioning. So a scalable and customizable architecture of conditioning can help you simplify the connectivity between the real live hardware and the simulator. Test automation. Test automation is one of the best and most important part of your hardware in the loop or digital twin configuration, because it allows you to use all of the time available. Even if your engineers aren't working, technically the test bench can perform the test. Also, by using the technology of hardware in the loop and digital twinning, you remove a lot of the high voltage, high power components that will require mostly supervision to ensure that there's no damage, no explosion, for example, for batteries. So by replacing them by your system here, by a hardware in the loop platform, you can ensure to do test 24/7, 365 days a year, and your test engineer can only work with the reports and the data that your system has been generated automatically. Now we understand that today's difficulty is finding resources. Every company is short on hands. So engineering services are offered by Cercia and OPAL-RT alike. And finally, as a proof of today, our partner network is pretty extensive at OPAL-RT, with partners like Certia, for example, that serve a lot of the European market. We have some that work on the North American market and in some others area of the world, as well as suppliers that work really well with OPAL-RT that are open to custom design components for your current application, because we all know that you're working for the future of aviation. So usually what you need does not exist necessarily. So the capability of customizing and building what you need for your application is something very important for you. So we have that with our partner network. So finally, it's the question period. I invite you to put your question inside the question and answer box of Zoom. In the meantime that we have questions coming in, I wish to invite you to visit OPAL-RT's website, OPAL-RT/Take Flight with HIL, which will present you the 2 other Take Flight with HIL webinars that will be held in October and November. And that way you can also register online through that website if those topics interest you. Ashol, we have a question for you that came in. So if you allow me, I'll read it for you. So
I saw it, the question.
Perfect. So why did you choose to implement a mixed Iron Bird?
Mixed Iron Bird, and what was the challenges? So I think that jump from 100% physical system to 100 virtual is not, it's not easy. So we have this intermediate level, and with this kind of installation, still we have a physical part on your system, and this physical part will correlate also the virtual or the digital parts on my Iron Bird. That means I will verify, because we have the actuators on the right side and where I have the models on the left side, so I can correlate the response and the dynamical behavior and so on. So it's more suitable to have this intermediate level in order to assess all this process. So and I think that the future will be 100 simulators as digital twins or this kind of technologies. In terms of challenges, we have to challenge, the real-time system. We have many constraints as the performance of the hardwares, the sample time, for example. We need to have a the height sample time levels and so on. So it was the first experience in this scale dedicated for this kind of facilities, Iron Bird, which is a standard facilities in order to qualify the equipment to be integrated on the aircraft. So that is the different challenges, and I think that this first experience, which is a real one and practical one, allow us to make more and more to deploy more and more these technologies for our the next generation of Iron Bird and the facilities, as I explained during the presentation. And thank you for the question.
Sure, if I understand correctly, it's also tied to the certification effort for the certification body, because right now, if I'm not mistaken, the regulation is still not allowing 100% simulation, right?
Yeah, but the regulation change thanks to the new challenges, and also we have to see that now the simulation tools are more mature than I think 20 years ago. So we have this this evidence that the models have the same behavior with the physical system. So the process is changing, and they are open. In the case of the aircraft, the regional aircraft, we have this issue of certification, but finally we did it.
Yeah, well, pioneer project like yours is actually opening up the way for the certification body to see and change the regulation since you have
Exactly,
the correlation with your program.
exactly, yeah.
Yeah, awesome. We have a question pertaining to if the webinar will be available offline. If I recall correctly, the answer is yes, it will be. It will be available through our website once the whole series will be done. So you'll be able to review it at your leisure around November. Another question that we have, can you explain more details on test automation? Do we separate test tools from automation or user has to automate test in Python? So perhaps we can do a double answer. So Ashur, if you allow me, I'll answer on the OPAL-RT side. And after that, if you can discuss how Certia manage automation, I think it will be interesting for everyone.
Yeah, for sure.
Awesome. So let's start with OPAL-RT. So OPAL-RT, since we offer multiple type of platforms, so with the National Instrument platform and the OPAL-RT platform, there are different strategies tied to the different tests and automation tools that both platform offers. So on the NI platform, we have Testan, that is a scripting environment built by NI. But on the OPAL-RT platform, we have the capability of scripting on different types of software and use a different APIs, to be able to achieve that goal. So you may do scripting in Java, in C++, or in Python, whichever language is the best for you and your team, so as to be able to achieve that automation that you want to do. Pertaining with the API, it gives you access to the full control of the simulator, parameter control, and all the data acquisition. Ashok, if you want to chime in on how Certia manages this.
Yeah, also we have a special software which is called Cockpit, dedicated to manage this kind of installation. And we have some modules in the cockpit based on National Instrument tools. And we developed this possibility to script all the tests and to make the automation of all the procedure. Because as you know, we have to make what's called endurance test for many days, many
Yeah.
months. And just for information, the Iron Bird is here normally to make the test 1 year before the first flight. And before the Iron Bird, we have the other facilities that they have to run 2 years. Without, we have just to stop sometimes the test in order to check, the mechanical checks and something like this. But we need this module, and the test automation, of course, is a very important part on our program and our software.
Great. Thank you very much, Asho. Maybe before going to the other question, I may have one. It's since you're doing all of those tests preliminary, since it was a demonstrator program, is there a different on the different steps that you have on your demonstrator program than you would have on a standard program? So is it shorter? Is it longer? How does it work?
You are speaking about the development of the program?
Yeah, well, like for example, the test that you've performed for, let's say, the Airbus 280, there were a lot of the parts to make it safe for flight and validated for passenger
In
travel
general,
with passenger. Yeah, go
yeah,
ahead.
in general, this kind of test is standard one. We have the regulation. We have to check the boxes in order to qualify the different. So we have similitude between the different testing. It's like a standard one, not very specific, because we address, the aircraft. Even we have small, big, or one, but the process still the same.
Okay. Thank you, Sho. We have another question for you. You mentioned a reduction of 40% in testing time. Could you please explain how you estimated this number?
Because we are provided of test rigs since 25 years. So we have this, this knowledge about what is the cost and what it takes time to make Iron Bird. So it's based on our previous experiences.
Okay. I presume the size of the aircraft should have also an impact on the time to test it because there's more component to it, right?
More components sometimes, yeah, but we have the same function, you know. Sometimes we have more actuators. We don't have enough the same size for the A380, for example, or the A320. But in terms of effort, sometimes we have the same effort, you know, because and the cost, yeah, the cost of the installation is different because we have big surfaces, big actuators. So we have a heavy mechanical part, but that is the advantage of the real-time simulation digital twin, is to win this kind of uh, of uh, uh, of manufacturing of this part of physical, because in terms of performance or dynamical behavior, have a big inertia on the test rigs and the big stiffness, something like this. So we have to make what is called eigenvalue analysis, something like this. We don't need to represent physically because we master the process, you know. It's just have a big thing. Sometimes we need this kind of physical installation as the picture of our capabilities, but I think that it's changing, and the trend is digital twin, virtualization, real-time systems.
Thank you, Asho. Next question is for me. Do you provide a fully integrated solution to specific project needs? We actually do. So if I roll back to our previous slide here, what you see here is a fully integrated test bench for air management systems. So you see at the bottom, it's just here. It's what we call an airing chair that can be swapped in, swapped out to address different type of different type of controllers. And you see at the top, there are actual real life actuators from the aircraft that have been installed into the system. Unlike Certia's program, which is the Iron Bird, so takes more space and is very uh, not embedded, but the control, the contrary, it's more like present and physically big. On those type of test benches, since it's a system test station, it's more compact. We can put the different components inside the bench and not necessarily respect the length of cables or the somewhat the position compared to the other components of the aircraft. So that's how we do it for specific project, and to be able to take less space and do very specific validation depending on your project needs. Pertaining to Ashur, even though if the question was directed to me, I would like to know, Certia does also offer specific project application solutions, right?
Yeah, yeah. It's you know, it depends on the request of our client. So we are integrators of solution, so we can provide many services around the testing, around you know the verification, around the certification. Depend on you know the customer. We have some standard product, but we can respond for all the customer requests.
Excellent. Thank you very much, Asho.
You're
We don't have any more question. I'll wait perhaps a little bit. In the meantime, I'll do a quick reminder pertaining to our new webinar that will be held on October 24th, sorry, which will be titled Future-Proofing Your Aircraft HIL with Electrification Capabilities. So basically more electrical components inside your aircraft or full electrical aircraft components. So please register. You have the link online in your screen presently at OPAL-RT.com. Thank you very much, everybody. Oh, we have a question. Can you share specific model and details about? I'm not sure exactly what the question means, but I'll start answering. And if Mr. Nagar, it's not answering you, please do put some more details into the chat, and I'll make sure that Ashur and I are complementing. But since most of the applications that we have are very customer driven and very applicative, it's very difficult to be able to share specific models with anybody, in a sense that, for example, OPAL-RT works with a main propulsion engine manufacturer most of the model are, or the big components of those models are provided by those suppliers, those customers. So obviously it's a proprietary information that we cannot share. But this being said, there are a lot of libraries, for example, in MATLAB, that are available for you to use and complement some of the libraries. OPAL-RT has also a full complement of electrical motors and inverter models already existing. So that way, if you don't have yours, for example, yet, you can use our more generic models to be able to parameterize the setup to be the closest possible to your application and your future motors, to be able to start your test even though it's not necessarily complete. So that way you can have the components start validating control algorithms, for example, without having the full motor digitalized at this stage. So we do offer those type of libraries. You can see them on opalrt.com, or if you do a search for the OPAL-RT wiki, we have all our products user guide available online. You just need to create an account, which takes about like 1 minute, and you will have access to those details and see the different libraries and different motor blocks that we have available for you to work with. Ashok, I don't know if you have something to add to this, if Certia has libraries or example models that can be used.
No, we in general we use the platform like MATLAB Simulink in order to to modelize the controllers. We use also AMSIM from Siemens, which is the program for the multi-physics systems. And after the model, after we get the model of our actuator, for example, landing gear or aircraft, we can make the model of just one component or integrate many components. We convert the model to the real time because we have a specific toolbox for that, and after that we can upload the real time model on the computers or the controllers, because we have dedicated the product from Opal. We use the Opal depend on the performance we need, so we have to choose the reference, because the choice of the hardware depend on the number of input output, or the number of the performance requested, and so on. And after that, we have a system ready to be used with the interface with environment. That is the process, and it's not the complexity of the model which is an issue, because it takes more and less time to make a model. But the process is like this. We have many examples of this application. We don't have just one specific model, but that is the philosophy.
Yeah. Okay. Thank you very much, Asho. Hopefully, Mr. Naga, we have answered your question. I presume we did, and we don't see any add-on question. So it's 10:46. I think we can conclude this session. Obviously, we will always be available for future question through our different web portals, being certia.fr or OPAL-RT.com. And please feel free to reach out to us if you have more question, or if you have a program or a project that you think we can help you out with, or you just have like generic question. We'll be more than happy to support you in your HIL endeavors. And again, just a quick recap, recall part 2, future-proofing your aircraft with the electrification capabilities, October 24th. Please come in numbers. Thank you very much. Have a great day, everyone. Thank you for your presence.